Welcome to practice number 123, and today we're talking about how the turbulence intensity level affects a NACA 0018's airfoil's performance at low Reynolds numbers. So this is a very important range because this is where the turbulence intensity level and surface roughness do affect the performance of a lot of airfoils at low Reynolds numbers. And the reason why is because at low Reynolds number, this is where the turbulence that is created by either the surface roughness or introduced by the turbulence intensity level or by the Reynolds number really has a major effect because the flow is laminar/transitional. If you go to very high Reynolds numbers, then the turbulence intensity level is not nearly as important because the flow is already very turbulent, and that already means that it's acting in the way that it should, and increasing the turbulence intensity level doesn't really change that characteristic too much. So this is a very interesting region of Reynolds numbers to look at. And to look at this topic, we're going to look at a paper called Numerical Study of the Effect of Reynolds Numbers and the Turbulence Intensity on the Performance of NACA 0018 Airfoils at the Low Reynolds Number Regime. So this is an open access paper. You can find it in the link in the description. And we're going to split this into two podcasts again. The first podcast is going to be mostly about the theory behind it and the CFD setup. They're using CFD here. And the CFD setup is actually really good. Like, they've looked into a lot of different aspects, some aspects which a lot of people don't even consider. So that is going to be quite nice. The other podcast, the second podcast to this series, is going to be discussing the results. So let's move on with the first podcast here. So in recent years, there has been an increased interest in small aircraft and small wind turbines. From the point of view of simplified approaches, a significant problem is the working conditions in which these devices must operate. One of the key quantities determining these working conditions is a Reynolds number and turbulence. The Reynolds number experienced by the airfoils of small wind turbines or UAVs can range from tens of thousands to several hundred thousand. And so in this range, the characteristics of the boundary layer are going to be different. So at low Reynolds numbers, the boundary layer is going to be more laminar, and small disturbances will have quite a big effect. Whereas if you go to very high Reynolds numbers, like close to 1 million, small disturbances are not going to be nearly as effective. So these are not conditions encountered in traditional aviation. However, in the case of turbulence, the problem is that different turbulence intensity levels are found in wind tunnels and real operating conditions. So generally speaking, a value that is less than 1% is considered to be of low turbulence intensity, whereas a value more than 10% is considered to be of high turbulence intensity level. In the case of modern low turbulence wind tunnels, the turbulence intensity of undisturbed flow can be even less, so 0.05%, and that's really low. So most wind tunnels around the world, aerodynamic wind tunnels at least, they will hover around 0.1% to about 0.9%, below 1%, with a lot of them being around 0.5, 0.6%, and that's quite low. Once you go into atmospheric wind tunnels, then you're going to be at about 5% or higher. So the turbulence intensity measured in the atmosphere is usually from a few to several dozen percent, so up to 20, 30% perhaps. The aerodynamics of a vertical axis wind turbine rotor is even more complicated, as its blades constantly operate under varying flow conditions. As the rotor rotates, the angle of attack of the airfoil changes, and thus the local Reynolds number also changes. During the operation of the rotor of the Darius wind turbine, that's where the blades are vertical, the rotor blade works with variable turbulence intensities. This is due to the slowdown and disturbances of the airflow by a blade moving in the upwind part of the rotor. So in other words, a wind turbine is quite different from a lot of other airfoils in that the wind turbine blades are going to have to sweep through wakes of the upstream wind turbine blades and or the central supporting shaft. So that means you have quite a dirty flow that's hitting these airfoils constantly, which means that you effectively have like an artificial turbulence intensity level being introduced. And it really depends on what angle the wind is coming at to a large degree. But regardless, you're going to have some sort of wake hitting the blades quite consistently, and that's potentially a problem. In the downwind part of the rotor, the blade already works in some highly disturbed flows. So in this paper, they're looking at a NACA 0018 airfoil, which is a fairly thick airfoil and is symmetrical. This paper discusses the performance of this profile, considering Reynolds numbers from 50,000 to 200,000, and turbulence intensities levels of ranging from 0.01% to 0.5%. So this is a very low Reynolds number range. Also, the turbulence intensity levels are quite low. Like, to get a premature trigger of turbulence to go into a turbulent boundary layer, a turbulence intensity level of higher than 0.5% is probably going to be needed, like 2%, 5%, something like that. So having very low turbulence intensity levels are quite restrictive as well in terms of the study. So looking at very low Reynolds numbers and low turbulence density levels. They don't talk about the surface roughness, but because of CFD, often there's it's either going to be smooth or there's going to be some sort of factor that they will use, which is the default setting. So the numerical results of the aerodynamic force coefficients of the symmetric NACA 0018 airfoil shown in this paper are primarily intended to serve as input data for analytical approaches dedicated to various wind turbine rotors. Even though the NACA 0018 airfoil was designed relatively long ago, it is still prevalent in vertical axis wind turbine designs because of the balance between the structural integrity and aerodynamic efficiency. So report number 568 from the NACA organization, which is the organization that came up with all these airfoils, and that's a prelude to NASA, published in 1937, this report, which presents the NACA 0018 airfoil performance measured for the Reynolds number regime from 40,000 to 3 million. The characteristics of the lift coefficients presented in this report, show some, though slight, dependence on the Reynolds number, and that's well known today. Like, we know that the Reynolds number does significantly influence the aerodynamic characteristics of an airfoil. But back in 1937, they were still just finding this out. This was really cutting edge. A much more significant effect of the Reynolds number was observed for the drag coefficient. In the case of the largest Reynolds number analyzed by these authors, so 2.97 million and 2.36 million, and almost independence of the lift coefficient from the Reynolds number in the linear part of the CL alpha curve is observed, and a slight influence of the Reynolds number on the drag coefficient is seen as well. So why is this? Well, the reason is because if we have an airfoil, and it doesn't really matter what angle of attack it is, but there are some differences to some extent. So let's say we have a low angle of attack to begin with. That's pretty high, but let's say it's about 5 degrees. If you're just listening to this, you can see the video on Spotify and on YouTube. So let's say it's 5 degrees. The flow goes over it. If we have a very low Reynolds number, it means that the flow is going to separate potentially, and we're going to get quite a large wake. That's going to result in the lift coefficient dropping and the drag coefficient increasing. If we have a high Reynolds number, then the flow will be able to stay attached longer, and we'll get a much smaller wake. So the lift coefficient will now start to increase more, and the drag coefficient will reduce because that wake is smaller. That's what the Reynolds number does. As you hit a high angle of attack, this gets exacerbated. So at high angle of attack, we know that the flow over an airfoil will be more prone to stall. And if we have a high Reynolds number, it means that the flow is probably going to be moving faster and or have more turbulence in it. So that's going to result in the boundary layer near the velocity near the wall going to be higher, which means that it can stay attached longer. And that means we get a smaller wake again, higher lift coefficient and lower drag coefficient. So that's what this means here. So a similar trend for the lift coefficient characteristics of a NACA 0009 airfoil for Reynolds numbers in the range of 3 million to 6 million can be found in the well-known report Summary of Airfoil Data from 1945. So NACA 0009 airfoil is a symmetrical airfoil, and it's very thin. It's only 9% thickness to chord ratio. Even though the Jacobs and Sherman results are more useful for the vertical axis wind turbine in general because of the low Reynolds numbers, but knowing what the characteristics of a NACA 0009 airfoil is very useful as well. So in 2019, some researchers published an important paper summarizing the collective results of experimental and numerical studies of this airfoil, the NACA 0018, for low and medium Reynolds numbers. A juxtaposition of the results of various researchers showed significant differences in the lift characteristics for Reynolds numbers below 300,000. This is important. It means that all these researchers who were studying NACA 0018 airfoil performances were finding different results. And this is where this paper comes into it. They say this is due to, among other things, the sensitivity of the flow conditions in the wind tunnel. Researcher Timmer concluded that the characteristics published in 1937 by Jacobs and Sherman might be affected by errors resulting from the high level of turbulence in the wind tunnel, which may significantly affect the transition characteristics. They probably would. Research by some other researchers also showed that the gamma theta turbulence model, so this is a turbulence model we use in RANS and URAN simulations. This provides sufficiently accurate aerodynamic characteristics for the NACA 0018 airfoil. As mentioned above, in the case of medium and high Reynolds numbers, its influence on their airfoil performance is not significant, which is also confirmed by observations by some other researchers. And sufficient accuracy of the results may also be ensured by, for example, the popular K-Omega SST turbulence model. In addition to the dependence of their foil characteristics on their angle of attack and Reynolds number, a dependence on the freestream turbulence intensity level is also necessary to define the reliable aerodynamic performance of vertical axis wind turbines. What does this all mean? So what they're saying is, so all these researchers that they were investigating their results, they were getting very varying data. And the reason why is not only because they have different Reynolds numbers, for example, but they have different approaches to modeling their CFD. So some are using, like, for example, the gamma theta terminus model, others are using the K-meg SST theta, that's the K-meg SST terminus model, others are using other things. What's more, we have the turbulence intensity level changing between all these different research campaigns. So we have all these variables that are not being controlled, at least not reported or implicitly controlled, and that can mess with the results, and they often do mess with the results, especially in this Reynolds number range. The reason why is because this Reynolds number range is very susceptible to laminar separation bubbles, and they are very finicky. Like changing just small parameters will change how the flow separates over an airfoil and how it transitions. In the previous podcast, I went through different transition mechanisms. There were 4 main ones that we went through, and if you want to check out that podcast, you will learn a lot about how boundary layers can transition, the different paths they can take, with the laminar separation bubble being just one of them. There are other ones as well. So I highly recommend that podcast here. So let's move on to the numerical result that they have, and so the numerical model that they have and its validation. So this paper aims to estimate the aerodynamic performance of the NACA 0018 airfoil at different values of turbulence intensity in undisturbed flow and at different Reynolds numbers. So first of all, they have the numerical domain and CFD solver settings. These are very important, obviously. Let me zoom out a little bit so you can see the entire picture. So as shown in figure 2, simulations were performed using a C mesh surrounding the NACA 0018 airfoil and extending 7.5 chords from the semicircular edge of the domain and 15 chords from the vertical edge of the domain. So what does this all mean? So this is a very common domain setup, and it's actually a very good one. So we have at the front, the inlet is this C shape. It's not like a typical flat surface. Well, it's like vertical flat surface. It's a C shape. And the reason why this is important is because it greatly reduces not only the computational aspect of different angles of attack, but also the variability. So if we had just like a regular rectangular box, and we have upstream, we have the inlet, if you go down to the corner, and at 0 degrees, it's fine because the flow coming in is directly parallel to the boundaries at this, like the top and bottom surfaces. But if you have the angle of attack go to 10 degrees, for example, or even 5 degrees, now when you go down to one of the corners, one of the boundary conditions, like the top or bottom, the flow coming in will now be at an angle to that, and there will be probably separation around that corner because that corner is not an inlet. That top and bottom surface, they're not inlets. They are either like pressure, like they're symmetry planes or pressure surfaces or whatever, but they're not inlets. So you have different conditions on that surface, so you're going to be getting errors. To get around that, the C mesh is very beneficial to use. And to use this, what we actually do often is we actually pitch the airfoil at different angles of attack, and or we put the inlet velocity at different angles of attack. So there's one way which you can just change the mesh every time. You like just remesh the airfoil at different angles of attack. Or you can simply just go back to your solver settings and go, okay, I want the velocity to be now, 5 meters in the X direction and 2 meters in the Y direction, which will give me an angle of attack of whatever it comes out to be. So that's a very easy way of doing that without having to remesh your setup. So that's very simple, but also accurate. So that's what they're doing here. One question is, how far downstream should the airfoil be from the inlet, and how far downstream should the outlet be from the airfoil? And these are going to be covered in this paper as well, which is why we're going through it here. And it's quite nice this way. So they say that the airfoil surfaces are treated as non-slip walls, so 0 velocities are ensured on the airfoil surfaces. This means that the boundary layer will grow on it, as you'd expect. And moving on to, based on the previous research and all the results presented in this paper, the time step size was assumed to be 0.0001 seconds. So this means that they're using URANs. For the transient solution using the implicit formulation, ANSYS fluent CFD codes require multiple iterations to be specified at each time step. So what does this mean? So if we have, like let's say you have time step 200, and the solver, like the CFD simulation, has calculated that. Instead of moving to time step 201, we actually do inner iterations to make sure that the solution has like stabilized a little bit, and then we move on, because when we change the time step, the flow obviously changes quite a lot. And we want to make sure that we don't get too many, like in mathematical terms, we don't want the gradients of the different flow conditions to be different flow parameters to be too great. We want them to be quite low, which means that the flow is not changing too much compared to our time steps and or when we're changing the flow. So to get the flow to be more stable, we want to have inner iterations every time step to make sure that the flow is sort of converging before we move on to the next time step. This is just a way of ensuring that our simulation doesn't crash. It will converge over time. So here they are using 10 to 15 iterations per time step, and a maximum of 20 maximum iterations was specified. And they have a level of residuals of 10 to the minus 6, which means that once the parameters, the changes in parameters get below 10 to the minus 6, they say that, okay, the simulation is converged. So that's quite low, that's quite good. Now we talk about something which is quite interesting. They say an important problem in time-dependent analysis is the effect of the initial conditions. In the initial phase of the simulation, the oscillations of the aerodynamic forces are significant, and the values of these forces differ significantly from the final ones. So this is a quite problematic statement, I think, because they say an important problem in time-dependent analysis is the effect of initial conditions. So you can look at this from a few different ways. The most basic way is saying that your initial conditions change your final result. That's not necessarily true. I mean, the basic assumption of CFD is that your initial conditions don't really matter as long as the flow converges. Now, obviously, you want to get good initial conditions because that will allow the flow to converge more quickly, and you have a higher chance of the flow converging. But as long as the flow converges, it doesn't really matter what your initial conditions were because they'll reach the same result. That's an assumption of CFD. So that's the first thing that pops into my mind when they say this, and it sort of contradicts what they're saying here. But when they say in the initial phase of the simulation, the oscillations of the aerodynamic forces are significant, and the values of these forces differ significantly from the final ones. So they might be referring to the convergence side of the CFD. They're saying that, okay, maybe the oscillations are so great that if we have very wrong initial conditions, the CFD may just crash straight away, and that definitely is a problem. But I'm not sure if that's what they mean here or not. I'm wondering if they mean that like having different initial conditions will result in different converged solutions, which it doesn't happen. So I'm not sure what they mean here. Maybe I'm reading this differently to how they intended. If you have any other ideas, let me know in the comments below. Let's move on here. So computing domain size effects. So as mentioned above, the size of the computational domain is an essential aspect of CFD calculations. Some authors pointed out that the influence of the domain size on the accuracy of the calculated airfoil characteristics depends on the type of mesh, e.g. C mesh or O mesh. So this is that domain size I was talking about and its shape. A review of the literature shows that there is no consensus on the size of the computational domain concerning the length of the chord. This applies to both airfoils operating at low and high Reynolds numbers. Some researchers employ small computing domain sizes. So in other words, you have the airfoil in there and you have a very small domain around it. So you might have the airfoil like this, and then the domain is like only this big. So you're going to get a lot of influence from the walls onto this airfoil, and the lift coefficient and the drag coefficient are not going to be very accurate at all. So some researchers do that, they say. In this case, the distance from the obstacle to the domain's boundary is from several to dozens of airfoil chords. Conveniently, the domain area in the wake region is longer than the distance from the inlet to the obstacle. And this is very standard. So they have the airfoil closer to the inlet compared to the outlet. And this is because of the wake of the airfoil. The wake needs to develop properly so you can have not only the lift and drag being right, but also the upstream effects that this wake has to be correct as well, because you have this feedback mechanism as well. So having a decently sized outlet, so it's far away enough from the airfoil, is a good idea. But also you want to have the airfoil quite far away from the inlet as well, because you do have these upstream effects that I mentioned earlier. So they say here, some researchers create computing domains of huge sizes. Sometimes the distance from the leading edge of the airfoil to the boundary of the computational domain is even several hundred times larger than the airfoil chord length. And that's good if they can do that, but sometimes it's overkill. Here they say paper 6 discusses the effects of 3 domain widths, 3.75 chords, 7.5 chords, and 15 chords on the characteristics of length of lift and drag coefficients. The authors concluded that the domain width does not significantly affect the airfoil's aerodynamic characteristics. However, the drag coefficient is more sensitive to the changes in the domain width than the lift coefficient. A numerical domain with a width of 15 chords here are used because it gives acceptable results. At the same time, the number of mesh nodes is half as compared to the mesh for the domain twice as wide. So you save on computational time, really. So that's what they're using here. They're using a domain width of 15 chords. So in figure 3, they talk about the effects of the length of the domain, so the distance from the inlet to the airfoil and from the airfoil to the outlet on the lift and drag coefficients. They say here that the length of the computational domain in the wake area behind the obstacle is also an important aspect for safety calculations. Therefore, the authors of this paper decided to verify the numerical model for several different lengths of the computational domain. So they're going to look at how increasing this domain size changes these lift and drag coefficients. For this purpose, 4 computational domains of different lengths were developed. The variable in these analyses is the length measurement from the airfoil's trailing edge to the domain's outlet, as shown in figure 3a, so here. The distance from the leading edge of the airfoil to the inlet was the same for all of the analyzed cases. Since the range of angles of attack ranged from 0 to 10 degrees, the numerical model was verified for 2 angles of attack, 4 degrees and 10 degrees here. So they want to just go across a few different angles of attack so they can validate it for the rest of their setup here. Thus, that's quite good. Like, they're being quite thorough here. A lot of aerodynamicists might only take like one angle attack, but they're doing 2 here just to be a little bit on the safe side, so that's good. So the analysis of the effect of the length on the aerodynamic characteristics of the NACA 0018 airfoil was carried out based on 8 test cases. The change in the length of the computational domain results in a change in the number of finite volume elements. So in other words, the amount of mesh cells you have. For the lowest domain considered in this paper, and the number of mesh elements was 8 million, while the largest was 9 million. So that's not really a huge change, but I guess it's better than nothing. So 20 seconds of air movement was simulated for each test case. In addition, a Reynolds number of 150,000 and a turbulence intensity of 0.25% were used to verify this numerical model, taking into account both the range of Reynolds numbers as well as the range of turbulence intensities, and that is analyzed in this paper. The values of these Reynolds numbers and turbulence intensities used for this verification process is more or less the average value. So in other words, they're trying to pick the middle of the road values that they're using in this paper for the rest of the paper, just to validate this domain. So looking at the average turbulence intensity level of 0.25% and the average Reynolds number of about 150,000. So the results of the numerical calculations of the lift and drag coefficients are presented in figures 3b and the way that they've presented these results in figure 3 are pretty cool. Like, they have the different lengths of the domain, and that's going to change the lift and drag coefficients a little bit, but they have different angles of attack as well. So they have these angles of attack, the values of the lift and drag coefficients normalized effectively by moving them down, so we can see the general shapes of these graphs. So they are comparable this way. So they say the results compiled in this way show that the numerical results of the coefficients differ very little for a given angle of attack. For an angle of attack of 4 degrees and a length of 14 chords downstream, so the outlet is 14 chords from the airfoil's trailing edge, which is quite a long way. The drag coefficient changes only by 0.28% compared to when the length of the outlet is only 10 chord lengths downstream. So in other words, this length, it doesn't really affect the drag coefficient too much. It's like 0.3%, which could really be just error based on different meshes, really. Figure 3c shows that in contrast to the drag coefficient, as the length of the computational domain in the wake region increases, the lift coefficient increases. However, this increase is also slight. For an angle of attack of 4 degrees and the length of 14 chords, it is only 0.26% different to when the length is 10 chords. So again, the lift and drag coefficients are fairly independent of this length here. They've got to the point where the outlet is far enough away that the lift and drag coefficients are fairly independent now. So for the angle attack of 4 degrees, the increase in the lift to drag ratio for the case of 14 chords downstream is also only 5.4% compared to when the outlet was 10 chords downstream. A further increase in the parameter of this length, so how far the outlet is, from 14 cores to 20 cores, causes only an increase in the drag coefficient, so the drag ratio of 0.11%. So in other words, at 14 chords downstream, the outlet from the trailing edge, the lift and drag coefficients are pretty much independent now. You don't really have to get a bigger domain. So they've now looked at this domain size and they've validated that domain size of this proportion is adequate. So they can move on now. So that's quite nice. That's what I mean by the CFD study. They did a pretty good job at looking at the different variables and seeing which ones are important and how to validate that they have the right variable selected. So what about the turbulence density effect and mesh sensitivity studies? One of the key achievements of this paper is the analysis of aerodynamic performance of the symmetrical NACA 0018 airfoil in relation to the turbulence density level. As a result of numerical dissipation, the turbulence density just before the airfoil is sometimes completely different from the turbulence density assumed for the boundary conditions. So in other words, in CFD, we specify a turbulence density level at the boundary, but once the flow gets to the object, because of dissipation, and viscosity and whatever, the turbulence density level will be lower. So we don't really know what the turbulence density level is at the object. We've specified it at the inlet, let's say 1%. By the time it gets to the object, it might be 0.5%. So it's not really what we're looking for. So this is potentially a problem. So this analysis aims to find a correlation between the turbulence density at the inlet and just before the airfoil. The different types of boundary conditions available in CFD codes require different flow parameters to be specified. In this work, the velocity inlet boundary condition is employed in figure 2a as shown. In the current investigation, two turbulence quantities are specified at the inlet, the turbulence density level and the turbulence length scale. I'm going to cover what these two different things are right now. The turbulence density is determined as the ratio of the root mean square of the velocity fluctuations to the average flow velocity. So in other words, you have the average flow velocity of, let's say, 10 meters per second or whatever. If the fluctuations are 0.1 meter per second, then we can say it's 10%. So, sorry, 1%. So we do that through the root mean square process, which is not a difficult thing to do. We've gone through it in other podcasts. So that's the turbulence density level. The turbulence length scale is something different, and it is very common. And this is the quantity that is appropriate to the size of the large eddies which contain energy in the turbulent flow. So in other words, you have this turbulent flow, you have all these vortices. What are the size of the vortices that contain most of the energy? All vortices contain energy, but the bigger ones typically contain more of them, more of that energy, like 90% perhaps. So we're looking at the turbulence length scale is approximating the length of these eddies or these vortices. So many reports from experimental measurements in wind tunnels only provide information about turbulence intensities at the location of the analyzed obstacles. So if you have, let's say, a ball in a wind tunnel, you take the ball out and you put a hot wire where the ball is, and you measure what the turbulence density is there, and you say, okay, that's what the turbulence density is at the ball. With CFD, you don't really do that. You go at the inlet, the turbulence density level is this, but once it gets to the ball, it might be different. So that's what they're saying here. It is very often the only turbulence parameter measured during experiments, following the guidelines available in ANSYS film documentation. In the case of wall-bounded flows, it is recommended to calculate the turbulence scale from the following formula. So the turbulence length scale is 0.4 times the boundary layer thickness. So in other words, 40% of the boundary layer thickness is the same as the turbulence length scale. In this current study, the turbulence length scale L was estimated on the airfoil to be 0.004 meters. So in other words, 4 millimeters. This paper does not analyze the sensitivity of the airfoil performance due to this parameter. A numerical experiment was carried out to investigate the rate of decay of turbulence intensity and determine the correlation between the turbulence intensity at the domain inlet and just before the airfoil. The analysis was performed for the following flow conditions. The Reynolds number was 150,000. The undisturbed flow velocity was 2.19 meters per second, and angle of attack was 6 degrees. In this study, 8 values of the turbulence intensity level were used: 0.1%, 0.5%, 1%, 2%, 4%, 6%, 8%, and 10%. Unsteady calculations were performed for 10 seconds of air movement, assuming a time step length of 0.0001 seconds. So let's talk about the results now in figure 4. So figures 4, B, and C illustrate the dependence of the turbulence intensity on the x coordinate. So in other words, as you go in the freestream direction, how the turbulence density level changes as you get to the airfoil's nose. Both points representing the start and end of the control segments are shown in 4A. Let's look at 4A here. So it shows we have the turbulence density set at the inlet, and as we go towards the leading edge of the airfoil, we want to know what the turbulence density level is and how it decays. And this is what these figures show here. Let me zoom out a little bit so we can see all of them together. There we go. Okay, so decay rate of this quantity is strongly dependent on the turbulence density that was set for the boundary condition. The higher the turbulence density level set at the inlet, the higher the decayed rate. So in other words, you might go, I want to get 5% turbulence density level at the airfoil inlet, at the airfoil nose, sorry. So I'm going to specify 10%, and then you go back to the airfoil nose and you see, okay, it decayed down to 3%. So I should almost double the turbulence density level to 20% perhaps at the inlet, but it's not going to be 6% turbulence density level at the airfoil nose. It might be like 4% now because it decays so rapidly. So the decay rate of this quantity is strongly dependent on the turbulence density level here, specified. The higher the turbulence density level, the higher the decay rate, as shown in figure 4b. In the case of the lowest turbulence density analyzed in this work, equal to 0.1%, the decay rate is represented by an almost constant function slightly dependent on the x coordinates. In other words, having a turbulence density level of 0.1% pretty much means that you have that same turbulence density level throughout your entire domain. It doesn't decay very much at all. And that makes sense because there's not much energy there to begin with, so viscosity is not going to be that high, neither is dissipation going to be very high. So it's going to stay fairly constant compared to the high turbulence density levels. But on the other hand, having high turbulence density levels, once you go to the airfoil, will be more likely to trigger a transition to turbulence in the boundary layer. So in the case of turbulence densities higher than 0.5%, the characteristic inflection of the turbulence density curve is visible. This inflection occurs approximately 0.5 chords from the first control point located at the domain entrance. So this inflection point that I mean is when you go at the domain inlet, so you then go half a chord downstream, you get this increase in the turbulence density level. Before this inflection, the turbulence density decay is much higher than after it. Near the nose of the airfoil, the turbulence density is very low for each test case. Therefore, to compare the differences in the turbulence density values in the vicinity of the airfoil, an additional chart was prepared in which the x-coordinate was limited to the last meter of before the airfoil, figure 4C. This is here. In the first case, it gives a decrease of 51.6%. In the second case, 95.3%. Well, okay, so even in this last meter before the airfoil, the turbulence density drops dramatically. This data can be used to interpolate the turbulence density level required at the inlet to obtain the expected turbulence density value for the airfoil. This data is shown in figures 4b and c, which can be used to interpolate these values that we need. So I've never really seen this being done for a CFD setup before. Like everyone just really just specifies what the turbulence density level is at the inlet, and they set it and forget it. They don't really look at how that decays through the domain. This is the first paper I've really seen do this, which is quite good, which is why I want to go through this. And we should really be doing this a lot more, I think, or at the very least use like these kinds of empirical data to infer what we should be getting for the inlet turbulence density level. So I quite like this. Well done for the authors. Moreover, a mesh density influence on the turbulence decay was examined. So in other words, how does the mesh density affect the turbulence decay? 4 additional meshes were prepared from an extra coarse to an extra fine mesh. Cases with the typical settings of Reynolds numbers of 150,000 and inlet turbulence density levels of 0.25% were prepared. Studies were performed for 2 angles of attack, 4 degrees and 10 degrees. All the results presented in Table 1 show the differences from the medium case upwards are tiny. So in other words, fortunately, having even more cells doesn't really change how quickly the turbulence density decays at this point. We've reached that point where the mesh is independent for this particular variable, so that's good. Therefore, they say it can be claimed that the mesh density influence on the turbulence decay is negligible. So finally, let's talk about the validation of the numerical result, of the numerical model, sorry. Figure 5, so let's move down to figure 5, shows a comparison of the aerodynamic characteristics of the NACA 18 airfoil obtained using a gamma theta Turbulence model for their RANs. And this is compared to some experimental data taken from Delft University that they published. The lowest Reynolds number published in this paper was equal to 150,000, which is fortunate for them because the CFD they've been running at as well is 150,000 Reynolds number. I'm guessing that's not by coincidence, but by design. So they have this experimental data to validate the CFD. Interestingly, the turbulence density level that the Delft experimental data is at is 0.02%. For their CFD, the closest turbulence density level that they used was 0.01%. So that's what they're comparing it with. It's slightly different, but it's close enough that there shouldn't be too many differences. Like in the lift curve slope at low angle of attack, there might be a little bit of a difference because of the LSB formation. I'm not sure. They don't really go into it here, but that is a possibility. So the graphs shown in figure 5 have the same scales as shown in figures 12 and 13, which is for the results section of the paper, which we'll go through in the next podcast. As shown in figure 5b, the drag coefficient results agree with the experiment both qualitatively and quantitatively. So in other words, they have the same kind of inflections along the angles of attack range. The absolute error of the minimum drag coefficient compared to the experimental data is only 0.0028. So that's like maybe 2-3% perhaps. I don't know what that comes out to be, but it's quite low. In the case of the lift coefficient, both series of results are sufficiently consistent with the range of angles of attack up to 6 degrees. Slightly more significant differences in the coefficients are observed above this angle of attack, and this is probably due to changes in flow separation. This effect is shown in the earlier work of these authors, as well as the studies by other researchers. One of the possibilities causing these differences in the effects not considered in these studies. So in other words, these studies are 2D compared to the experiments being 3D, so you're going to get slightly different results. So some include potentially induced drag and potentially three-dimensional turbulence over the airfoil. The second reason that we are getting some differences between the lift coefficient of the CFD compared to experiments is that the turbulence model is not calibrated through the model constants that control the characteristics of the separation bubble. So here they do say that there is a separation bubble happening. The gamma theta model, like all turbulence models, use coefficients in their equations. These are empirically determined, and they are not specific for this LSB formation for this study. You can get coefficients that are specifically designed for this LSB, but they don't have them here, and that could make a major difference. That's why we do get potentially some differences here in different angles of attack. At low angles of attack, that's probably what's happening. The LSB is not being properly modeled by the CFD compared to this experiments, but also the change in turbulence density level might have a slight effect here. At high angles of attack, that will also change if there is an LSB happening here. I'm not sure if there is. They're saying there is, but I don't see any CFD flow vis here. But if there is, that will change when the LSB is popping and potentially how the airfoil stalls. So that could happen here as well. So that's a good catch here by the authors here. So that's in this paper. In the next end of this podcast, in the next podcast, we're going to go through the rest of this paper. We're going to go through the results. In this podcast, we've just gone through all these different ways of setting up your CFD and checking if it is valid. So we've gone through your validation process. We've gone through how the turbulence density decays with time, which is really cool. I haven't seen that before. We've seen how the domain size changes the results and what domain size we need, and also the theory. So if you want to see more of this, check out other podcasts, and the next podcast will come out in a few days. And if you like it, make sure to give this a like and subscribe. And if you want to get better at CFD and or theory yourself like this, check out our courses in the link description. And I'll see you next podcast. Peace out, amigos.